Welcome to the 12th lecture of the course Discrete-time Markov chain and Poisson processes. So, today we are going to talk about what is called strong Markov property. So, earlier just recall that we have talked about what is called Markov property. So, what was Markov property? Just recall that, and then we will go for what is called the strong Markov property, and we will then discuss what is the main difference between Markov property and strong Markov property, and finally we are going to see one example where the strong Markov property can be used to solve the problem. Okay. So, just recall that the Markov property was as follows, that if I have a Markov chain Xn, if I have some fixed time m and I condition at the time m the state is I, then after the time m the Markov chain is starting afresh. Okay? Markov chain is starting afresh from the state I. Okay. So, that means that if I have the time horizon like that, the time is 0 here, then 1 and so on so forth, at some time I have the mth time. So, m is a fixed time. Okay. M is a fixed time, and if I write the state here, then state is I here, state is I here, then the Markov property tells us that, well, this part is independent of this part. Okay. Future is kind of independent, and the Markov chain is starting from here, Markov chain is starting from here. So, I just rescale this time to be 0 and so on so forth, then m plus 1 may be mapped to 1 and so on so forth, and that all the things, that probability, transition probability matrix remains same. Only thing is that initial distribution now is delta I, that means I am starting from I. Okay, that means I am starting from I, and then I am, the Markov chain is approaching to the time is approaching. Okay. So, that is basically the idea of the strong Markov property. Now, let us see in this case what I have pointed out, this m is a fixed time, this m is a prefixed time, actually prefixed time. So, it is not a random time, but it is a prefixed time, like m could be 1, m could be 2, m could be 3, it does not matter, but this is not a random time, it is a non-random time. Better word to give is the non-random time. Okay. So, now natural question is that what will happen if instead of a non-random time, if I take a random time, and strong Markov property talk about that. Of course, I cannot talk about any random time, I have to talk about a particular kind of time which is called stopping time. So, I will discuss that, but just for example, I suppose I take instead of m, maybe I take the heating time to the state I, because if at Ti I know the state is I, because this is the heating time, that is the first time I enter into the state I, starting from some non-I state. Okay. So, or if I start from I state I, then Ti will be 0, that we have discussed earlier. So, I know at Ti the state is I. So, the state is known at the point Ti, but Ti itself a random. Okay. Ti itself a random time. So, now if I replace this m with Ti, so that means if I have a time horizon like that and some Ti is here, now can I tell the same thing, that this part is independent of this part, or those kind of thing? Can we tell? Can we tell that the Markov chain start afresh from the state I onwards? Can we tell these things? So, this question is answered by what is called strong Markov property, and as I mentioned that, well, I cannot take any random time here, instead of m I cannot take any random time, but I have to take a specific type of random time, and that random time is called stopping time. So, what is stopping time? Stopping time of a Markov chain Xn is defined as follows. So, a random variable t, which is of course time in our case, random variable t taking values in the set 0, 1, 2, so on so forth and infinity. So, t can take value 0, t can take value 1, t can take value 2, so on so forth. So, all non-negative integer value it can take, along with it also can take t equals to infinity. It can take infinity value also, just like heating time. Heating time can take value 0, take value 1, take value 2, and so on so forth. All for non-negative integer value it can take. Along with it can also take the infinity value if starting from state j, if I do not heat the state I, then the heating time of the state I will be infinity. That we have discussed. Okay, so t is a random variable which basically take values in this set, is called a stopping time of a Markov chain xn if following happens. So what happens if the event t equals to n is completely determined from the value of x 0 to xn. Okay, so this n is same as this n. So if I know what are the values of time point 1, time point 0, time point 1, time point 2, and so on so forth, time point n, I can tell what is the whether t equals to n has occurred or not. I can tell whether t equals to n has occurred or not. I do not need to know any information of the future. Only up to n I have to know to tell that whether t equals to n has occurred or not. Okay, so that means that t equals to n, this event can be completely specified, or that the event depends only on the random variables x naught to xn. Okay, x naught, x1, x2, so on xn. Only on this random variable, this is this depends on that. And note that this n is same as this n. Okay, this n is same as this n, and this particular thing has to be true for all possible non-negative values of n, 0, 1, 2, whatever the values of n, this has to be true. Okay, now intuitively speaking, what does this basically mean? This means, as I said, that if I say you to stop at t is a random time, I tell you to stop at t, then if you see the process up to the n, you can tell whether you have to stop at n or not. Okay, if you see the Markov chain up to the observed value of the Markov chain up to the point n, you can tell whether you have to stop at n or not. So that means, observing the observed value of the Markov chain, I can tell when I have to stop if I am asked to stop at the time point t. Okay, so let us see some examples, couple of examples. So first example is basically the heating time. Just recall that heating time we have defined as infimum of the set n greater than equals to 0, such that xn belongs to A, and A in this case a singleton set. So I can also write this way. Okay, so this was the heating time, and now you see that if I have suppose I have observed x naught to be j. If I observed x naught to be j, that means basically nothing but I can tell that I can easily say that tj is equals to 0. Okay, these actually equivalent sets, these two are equivalent set. So if I observed x naught equals to j, I can tell that tj equals to 0. So tj equals to 0 is completely specified by depends only on x naught equals to j. It does not depend on whether the future values are. Okay, what are the future values are. So if I take, in this case I have taken n equals to 0 here, and so tj equals to 0 is same as x naught equals to j. So that means this is completely depend on this particular event, and so this one hold true. Now what will happen if I take n is greater than or equals to 1? So now you say that tj equals to n. When we say tj equals to n occurred, that means starting from some non-j state, I hit the j state for the first time at the time step n. Okay, starting from some non-zero non-j state, I hit the state j for the first time at the time step n. Then we say this happens, and that I can write in this way, that x naught not equals to j, x2 not equals to j, so on so forth, xn minus 1 not equals to j, and finally xn equals to j. Again you see that if I know the values of x naught, x1 up to xn, then I can tell that whether tj equals to n has occurred or tj equals to n has not been occurred. Okay, so that means that in this case seeing this quantity, I can tell whether Tj equals to n has occurred or not, that I can tell, and that's why this Tj, which is the heating time, is also a stopping time. Okay, so heating time to the state j is always a stopping time for that Markov chain. Now let us take another example which is not a stopping time. So in this case, you see that what I have taken is that, suppose I take this definition, clearly this also can take values in the set 0, 1, 2 up to infinity, okay, in this particular set. Now see, in this case what happens is that if I have to see whether Li equals to n or not, if I have to see whether Li equals to n or not, then basically starting from 0, I have to know what happens in this part, whether the chain visits the state I here in the future after n or not, whether state visit I after n or not. If the chain does not visit I, then Tli equals to n. If the chain visits I after n, then it will not be n, it will be more than n. Okay, so to say whether this has occurred or not, I have to know what are the values of the Markov chain in the future to n. So that basically mean that this particular event now does not depend on only in this part, but it also depends on this part also. I have to know whether the Markov chain has visited or will visit the state I or not after n. Okay, so that's why this Li is in general not a stopping time, is not a stopping time, it is not is important. Okay, it's not a stopping time. So let us take another example which is intuitively make very sense. Suppose I am in a train, I am moving this direction, and there are 3 stations, station A, station B and station C. What I want to visit the station B. Okay, I want to actually leave the train, get out of the train at the station B. Okay, so this is my destination and I want to leave the train at the station B. Okay, now when the train has started from somewhere here and it moving, and I do not know, I am for the first time I am going here. Okay, for the first time I am going to the station B in this particular rail route. For the first time I am going there, and I do not know that when station B will come. Okay, so what I am going to do? I am going to ask my co-passengers that I will tell that, okay, please help me, and I want to get out of the train at station B. Please tell me when station B will come. So normal reply which come to us is that, well, you look for station A and station B is the next station to station A. So when station A will come, you just go to the door of the train and then it will come to, eventually it will come to station B, you just get out of the train. Okay, you just get out of the train. That is the normal answer we get from our co-passengers. Okay, now so if that information is given to me that station B is next to station A, that is fine with me. I will look for station B, station A. When station A will come, I will go to the door and then I will get out of the train at the station B. But suppose some co-passengers told me that station B is followed by station C. Then there is a problem. That is not a useful information to me, because I cannot get out of the train at station B if I have the information that station B is followed by station C. If I have only this information, then I cannot get out at the station B. And the idea of the stopping time exactly that if I know up to this, I can know whether I have station B has reached or not. If I can do this, then that information works as a stopping time. But if I cannot tell whether the station B is coming based on only this information, then that information will not work as a stopping time. Just the second information tells that, well, station B is followed by station C. From that I cannot get out of the train at station B, because I have to know the future to understand whether the next station is station B or not, and that is not at all a useful information to me. But if I am told that station B is next to station A, that is a important, that is a useful information to me, and that information can work as a stopping time, because using that I can stop at station B. Okay, using that information I stop at station B, but the other information that station B is followed by station C, using that I cannot stop at station B, and so this is not a stopping time information. Okay, so this information I feel that may be helpful to understand what is the stopping time. And now again visit these two example, that in the first case, given the information up to n, I can tell whether Tj equals to n has occurred or not. So that was that first example, this Tj is a stopping time, but in the next example Li is not a stopping time, because given up to the information n, I cannot tell whether Li equals to n has occurred or not. Okay. So with that idea of stopping time, let us move and let us see now what is strong Markov property. So again recall what was Markov property. In case of the Markov property, we know that if I have some time m and the state is I write time here, I write state at the above, then basically know that, then basically this part and this part kind of independent, and Markov chain start afresh from here. Now our question was that if I replace it m with some stopping time, and that is given here. So what it tells that, well, if I have some Markov some time horizon and t is a stopping time, and if I know that the state at the time point t is I, then you see that what happens, that information is given in this theorem. So it tells that, well, if Xn be a Markov chain with transition probability matrix P and some initial distribution, does not matter what is the initial distribution, and T be a stopping time for the Markov chain T. So this T is a stopping time. Of course, for the Markov chain, for this particular Markov chain. Okay. Then conditional on t is less than infinity and xt equals to I. So xt equals to I means that xt equals to I means basically state at the time point t is I. Okay, and I am taking t is less than infinity. If I do not take t is less than infinity, then xt does not make much sense, because t infinity does not make any sense. So this condition I have to take to make this quantity to be a meaningful quantity. Okay, that xt is a meaningful thing, that I take that t is finite. Okay, stopping time is a finite one. Okay, so it says that if t is less than infinity, conditional on t is less than infinity and xt equals to I, xt plus n for n greater than equals to 0 is nothing but the Markov chain in this part. Okay, xt plus n for n greater than equals to 0, it is xt, then xt plus 1, then xt plus 2, and so on and so forth. So this is nothing but the Markov chain in this part only. Okay, is a Markov chain. So this part, sub part of the original Markov chain is again a Markov chain. The sub part of the original Markov chain is again a Markov chain with the same transition probability matrix, and initial distribution is Ti, so delta I. So as if from I it is again starting afresh. So you see that the conclusion here and conclusion here are same. So that means even if I replace m with some stopping time, the conclusion remains same. And then also I have the independence is also there. So now this part is independent of this part. So x0, x1, xt, these random variables are independent of xt, xt plus 1, xt plus 2, and so on and so forth, under the condition that t is less than infinity and xt equals to I. So strong Markov property says that, well, even in the Markov property, if I replace the m with some time, some stopping time, the conclusion of the Markov property still hold true. And why we use this strong word here? Because it is stronger in the sense that instead of a fixed time, now I can take the stopping time also. Instead of a fixed time, I can take a stopping time also. Okay. So let us go through this once again, that it says that if I have a Markov chain with transition probability matrix P and whatever initial distribution does not matter, I have a time t which is, I have a random variable t which is a stopping type for that Markov chain xn, then if I condition with respect to t less than infinity and xt equals to I, that means t is a finite time and at the time point t the state is I. If I condition with respect to all these things, then the next part of the Markov chain is independent of the previous part, and this sub part of the Markov chain again is a Markov chain having the same transition probability matrix P, and the initial distribution is delta I, because at the point t I know that the state is I. So Markov chain is starting from state I, Markov chain proceed in time in future, and the sub part that from xt to or xt onwards, that part of the Markov chain is basically again a Markov chain having the same transition probability matrix P, but it start from I. Okay, start from I, that means the initial distribution is delta I, and the independence was also there, that the that xt x naught to xt, so that is basically the Markov chain in this part is independent of Markov chain in this part. Okay, so that happens. Okay, so let us proceed with okay. Now let us proceed to an example where I can use the strong Markov property to solve this example. Okay. So what is this example? The example start with the same idea of birth death process. Only thing is that here this probability of birth remains same for any state. Okay, from I to I plus 1 or I minus 1 to I remains same, whereas probability of death also remains same, it does not depend on I, the state I. Okay. So it is also can be thing of a generalization of the Gambler ruin problem, because in case of the Gambler ruin problem I do have some terminating state here, but in this case we are not assuming any terminating state as if it is going on in time. Okay, I mean it is basically I have infinite states, so the process can continue for infinite. The state can be anything, any positive, any non-negative integer can be state in this case. Okay. So in this case, what is our aim? Our aim is to obtain this probability. So what is this probability? We know this is nothing but the conditional probability that starting from 1, what is the probability that I hit 0 for the first time at the in n time step. Okay, starting from 1 I hit 0 in n steps. Okay, I hit 0 for the first time in n steps. That probability we try to find out. Recall that again this is nothing but the hitting time to 0. Okay, this is nothing but hitting time to 0. So it is starting from 1. What is the probability that for the first time I am entering into the state 0 in the nth step. Okay, in the nth step, that probability we try to find out for all values of n. So clearly that P1 T0 0 has to be 0, because starting from 1 in 0 step I will not be in 0. Starting from 1 in the 0 step I cannot be in 0. So that probability has to be 1. Then I am looking for what is the probability that T0 equals to 1, that I am looking for. I am looking for what is the probability that T0 equals to 2 starting from 1, that probability I am looking for, and I am going in. Okay, that is basically the thing we try to try to find out in this particular example. And as I said, we are going to use Markov chain, strong Markov property to solve this problem. So now to find out these probabilities, we are going to talk about what is called probability generating function. So what is a probability generating function? By definition, the probability generating function is this. So for any random variable x, if x is a discrete random variable, then I can talk about the probability generating function of x, and by definition this is nothing but for 0 is less than equals to s is less than 1, this phi of s is basically nothing but expectation of s to the power x. Okay? I try to find out this expectation for any s in the interval 0 and 1, 0 inclusive, 1 excluded. I try to find out this expectation. Now, clearly this expectation will be a function of s. This particular function is called probability generating function of a random variable. Now, in this case, because I am talking about the conditional probability, so I have to talk about the conditional expectation in this case. And if I write this one, it basically nothing but summation n equals to 1 to infinity s to the power n a p1 t0 equals to n. That can be written in this case also, that it is nothing but s to the power x into multiplied by x equals to x, and I have to take the sum over the support of x, okay, over the support of the discrete random variable x. So, same thing we are doing here. In this case, support is basically anything from 1 to infinity. So, I am taking the summation over this possible this particular thing. Okay, I am taking the summation that s to the power n probability under 1 under x naught equals to 1 t naught equals to n, that sum I have to take, and that will going to give me that probability generating function. So, what is the benefit of having probability generating function? There are many benefits of the probability generating function. So, probability generating function is a very useful function in probability, and the idea is that probability for discrete random variable, if I know the probability generating function, I know the distribution of the discrete random variable. Okay? If I know the probability generating function, I know the distribution of that particular discrete random variable. How? The idea is very simple from this part. You see that in this expression, the coefficient of s to the power n is nothing but the probability that t naught equals to n under x naught equals to 1. So, that means that coefficient of s to the power n is probability of t naught equals to n given x naught equals to 1. So, that means if I can calculate this particular function, then if I can calculate if I can collect the coefficient of s to the power n in this expression of phi s, then I know all these probabilities. Okay? Not only that, there is many benefits also. This is the first point. Second point is that if two random variables, if two discrete random variables x and y has same probability generating function, then x has same distribution as y. Okay? So, x, if two discrete random variables x and y have same probability generating function, then I can tell that x and y has same distribution. So, that means that if x has this distribution, these probabilities, then y also satisfy the same probabilities. Okay? So, two random variables, if I can show that two random variable has same probability generating function, then that two random variables has same distributions. So, probability of x equals to x is same as probability of y equals to x for all values of x. So, this basically implies that probability of x equals to x is same as probability that y equals to x for all values of x. So, that is basically the idea. Okay? Now, another point I should mention here is that what will happen if I take s goes to infinity in s goes to 1 in phi s. So, what is the limit s increases to in 1 of phi s? Again, you can see it from here. So, that basically mean that as if you can if I assume that I can take the limit inside of the sum, I can write it s increases to 1 s to the power n. This limit is only on this part, because the rest of the part does not depend on s. So, this part is 1. So, this is nothing but summation n equals to 1 to infinity probability p1 t0 equals to n, and which is same as p1 t0 is less than infinity, that I am summing over t naught equals to 1, t naught equals to 2, t naught equals to 3, so on so forth. I am summing the probability of these events, so that that is nothing but the p1 t naught is less than infinity, p1 t naught is less than infinity, t0 is less than infinity. Okay. So, taking this limit actually from here, I can also find out what is the probability that in finite time I will hit state 0 starting from 1. Okay. I can once I can find this particular thing, that probability generating function of t naught, I taking the limit as s goes to 1, I can also find what is the probability of hitting 0 in finite time starting from 1. If this probability is strictly less than 1, then there is a possibility that infinite time I will hit 0 starting from 1, that basically mean that I will not actually hit 0, and if this quantity is 1, then I can tell that starting from 1 for sure I will hit the time 0. Okay. And note that in this particular case, once I hit 0, I will be in 0 forever, because this is the observing case, that from 0 I can go to 0 only with probability 1. Okay. And finally, one more point I should point out here, that is basically that if I take the derivative of s, derivative of phi, if I take the derivative of phi, suppose I take the derivative with respect to s of phi, again if I assume that the derivative can be taken inside the summation, so that turns out to be n equals to 1 to infinity derivative of s n times probability p1 t naught equals to n. So, this turns out to be summation n equals to 1 to infinity, n is n minus 1, p1 t naught equals to n. Now, if I take limit s increases to 1 of phi prime s, which is basically nothing but this phi prime s, and again if I assume that limit can be taken inside the summation sign, that actually tells me that it is nothing but n p1 t naught equals to n, because this quantity actually goes to 1 when s goes to 1. Okay. So, now what is this? This is nothing but expectation of t naught starting from 1. Okay. So, few things, that if I take the derivative and take the limit, then I get the expectation, and if I take the limit without taking the derivative, that will give me what is the probability that in finite time I will hit 0 starting from 1. Okay. So, these are the some things we can look into the some characteristics of the Markov chain based on the probability generating function of t naught. And so, our aim here is first to calculate this probability generating function, and as I mentioned that once I get that, by collecting the coefficient of this, I can actually answer our main question. Not only that, with that we can also answer some other questions as a subproduct. Okay. So, let us move on to the next slide. So, now as I mentioned, now our revised aim is to calculate phi of s. Okay. Our aim now is to calculate phi of s. So, to calculate phi of s, I can proceed as follows. Suppose I start from state 2. Note that this is basically that starting from state 1, what is the expectation of this quantity. Okay. Conditional on the fact that I am starting from state 1, but to find out it, suppose I start from state 2, suppose the chain is starting from state 2, what happens? Let us see that. See, if I start from state 2 and if I have to hit state 0, then I have to move to state 1, there is no other option. Directly from 2 I cannot go to 0, I have to if I want to go from 2 to 0, I have to go via 1, there is no other option. Okay. So, that is why what I am doing is that, suppose this is the time 0 and time 0 the state is 1. When I have to go from 2 to 0, as I mentioned, I have to go via 1, that means starting from 2, first I have to hit 1, and suppose for the first time I am hitting 1 at the time t1, that is the our standard notation. So, here the state is 1. Okay. From 2 I start, from the state 2 I start at time 0, at the time t1 I hit state 1 for the first time. Okay. So, here no 1 has occurred, here 1 has not occurred. Okay. 1 has not occurred here, for the first time 1 occurred here. Then it goes on, and finally at the time point t0 I hit the state 0. Suppose this difference time is basically denoted by t tilde 0. This is the difference between t0 and t1. So, that means I can now write t0 as t1 plus t0 tilde. Okay. The time is t1 0 to t1, and then t1 to t0, which is the time t0 tilde. Okay. So, I can write in this manner. So, using the strong Markov property at the time t1, note that t1 is a stopping time, we have already proved. So, I can in the strong Markov property, I can use the strong Markov property at the time t1, and that is what basically I am doing here. And then what I can tell is that starting from state 2, the conditional distribution of conditioning on the fact that t1 is less than infinity, starting from 2, conditioning on the fact that t1 less than infinity, that t0 can be written as t1 plus t0 tilde, where t0 tilde is the time taken by the chain to hit 0 after t1. Okay. t0 is the time taken by the chain after t1 to hit 0. Okay. So, that means basically starting from state 2 at the time 0, I first hit the time state 1 at the time t1, and then t1 I finally hit state 0 at the time t0, and in between time I denote it by t tilde. And note that when I am writing here, I am implicitly assume that t1 is less than infinity. If this is not true, then this breakup does not make any sense, because t1 goes to infinity, then this breakup does not make any sense to me. Okay. Strong Markov property also tells us that this part of the Markov chain is independent of this part of the Markov chain. Okay. The future part, this is basically a Markov chain start afresh at the time 1. Not only that, this part is independent of this part. Now, t1 depends only on this part. Okay. t1 depends only on this part. So, that means that and this t0 tilde depends only on this part, because this is the time, t0 tilde is the time that starting from 1 hitting to t0. Okay. And that does not have any effect from here. So, that this says that t0 tilde and t1 are independent. t0 tilde and t1 are independent. Okay. Because t0 depends only on this, because this is the stopping time. So, this has to depends only on this, and t0 tilde depends only on this part, because this is the time taken by the chain, additional time taken by the chain to hit the state 0 after t1. So, that also does not have any effect of the states here of the chain here. Okay. This part of the chain has no effect of this part of the chain. These two parts are independent. So, and t0 tilde only depend on this part. So, that is why t0 tilde is independent of t1. Moreover, a very important thing is that the distribution of t0 tilde is same as starting from 1 hitting to 0. Why? The reason is that I have already reached 1 here, and strong Markov property says that the Markov chain start afresh here. Markov chain start afresh here. Only thing is that is starting from 1. So, clearly the distribution of t0 will be same as if I am starting from 1 and I am hitting to hitting to the state 0. Okay. Starting from 1, I am hitting to state 0, that is basically t0 tilde. So, the distribution of t0 tilde will be same as the distribution of t0 when I know x0 equals to 1. Okay. So, this basically I can use now to solve these informations. I can use that two information basically here, that one is t0 tilde is independent of t1 under the condition that this quantity is less than infinity, and that t0 and the distribution of t0 tilde is same as the distribution of t0 when I am starting from 1. Okay, these two things now we are going to use, and we are going to look into this. So I have expectation of 2 s of t naught, and that very loosely written can be written as t2 s of t1 plus t naught tilde. Okay. Now because these two are independent, I can write it as t2 of s t1 into s t naught tilde. Now I will use the independence, that this part is independent of this part, and if we know that if x and y are independent, then expectation of x y is same as expectation of x into expectation of y. Now in this case, if I take s to the power t1 is x and s to the power t naught tilde is y, then these two random variables are independent. So loosely speaking, I can write it is t2 s t1 multiplied by, now when I reach t1, now the Markov chain start from 1. So it is expectation of t1 s t naught. Okay, s t naught, that way I can able to write, and if I write in this particular manner, what I get is that you see that what was the definition of this thing, this particular quantity we have denoted by phi of s. Okay, sorry, not this one, we denote that phi of s is basically starting from 1 s to the power t naught. Okay, so this part is clearly phi s. Okay, this part is clearly phi s. Now what about this part? Now look into this Markov chain once again. So this phi s is basically nothing but starting from 1. What is the expectation of s to the power t naught? That is basically the thing. Okay, so starting from 1, the expectation of t s to the power t naught, that we have denoted by phi s. Now you see that starting from 1 hitting to the state 0 in n step is basically same as starting from 2 hitting 1 in n step. Why? The idea behind that is that here the this particular Markov chain, this probability of going right is p and probability of going left is q. So this p and q is fixed throughout. So it does not matter whether I am trying to find out the probability distribution of t naught starting from 1, or whether I am trying to find out probability distribution of t I minus 1 starting from I. Okay, whether I am moving from this to this or whether I am moving from this to this, the distribution will remain same, because for this Markov chain the probability of going towards left is p, does not matter from which state I am starting. Similarly, going towards left is q, does not matter from which state I am starting. Okay, so that's why this thing is true, and this is true for all n, for all possible values of n. So if this is true, then basically if you just go back, then I can write this quantity same as n equals to 1 to infinity s to the power n p 2 t 1 equals to n, and this one is nothing but expectation of starting from 2 s to the power t 1. Okay, starting from 2 s to the power t 1. So starting from 2 s to the power t 1, expectation of s to the power t 1 is also phi s, and you see that we got exactly that, the same thing here. So this quantity is also phi s, and then this says that this one is same as this thing. Okay, this one is same as this thing. So this one is same as this thing, and then so we got that starting from 2, expectation of s t naught starting from 2 hitting to expectation of s to the power t naught, which is t naught is basically hitting time to 0, is same as phi s square, if phi s is nothing but the expectation of starting from 1 the expectation of s to the power t naught, the conditional expectation of s to the power t naught. Okay, so we got this expression. Now we try to use this expression in the further analysis. So another point into looking into phi, so what we get that expectation starting from 2, the conditional expectation of s to the power t naught is same as phi s square. Okay, is phi s square. So now look into phi s from a different perspective. So by definition, phi s is that. Now what I am doing, I am using the Markov property, not the strong Markov property, the Markov property, because the time is fixed now. And what I am doing is that I am starting from 1, and from 1 I can either go to 2 or I can go to 0 in one step. So I am conditioning with respect to the first transition at the time 1. Okay. So from 1 I can move to 2, and that probability is p. So I can write this one is p times starting from 1, next transition is 2, then conditional expectation of s to the power t naught. Okay. Plus from 1 I can move to 0. So x naught equals to 1, given x naught equals to 1, x1 equals to 0, I try to find out the conditional expectation of s t to the power 0, okay, multiplied by the probability, which is q. Okay. Now look into this, first look into this expectation. This p is as it is here. Now look into this expectation. So this expectation means that x naught equals to 1, x2 equals to x1 equals to 2, and then under this condition I try to find out what is the expectation of s to the power t naught. Now when I move to 2, that means that Markov property now tells me that it can be that at the time point 1 the Markov chain is starting afresh. Okay, at the time point 1 the Markov chain is starting afresh, and at the time point 1 the state is 2. So this quantity can be written as this expectation can be now written as expectation that starting from 2, it is nothing but s to the power 1 plus t naught. So basically I reached 2 here. Now from 2 I have to hit state 0, but one step I have already taken. So this 1 has come here, given x naught equals to 2. So Markov chain as if start from here afresh. You just forget about this 0, forget about x naught that 0 time point, and as if time point started from here, then 0 1 2, rescale the time point from 0 1 2 and so on and so forth. So this expectation turns out to be that, and then s to the power 1 comes out here, that s comes out here, the rest of the part is written here. Okay. Now when x1 equals to 0, that means in one step I reach 0. So that means t naught will be 0, t naught will be exactly 1 in this case. That means that it will be nothing but starting from 1 s and s. So that expectation is s, because there is no randomness there, the expectation is s. So finally we get this, and this basically tells me, because beforehand we got that E2 s t naught equals to phi square s, I write that phi s is same as p s phi s whole square plus qs. Okay. So that means phi satisfy this particular condition. Just instead of writing phi s, now I am just writing phi. If I do this, it turns out to be this. Okay. This p s phi square, this is phi square, p s phi square plus qs minus phi is equals to 0. Now let us solve for phi. If I solve for phi using, because this is a quadratic equation in phi, if I solve, I get this particular solution. Okay. Note that we have two possibilities here, that positive sign or negative sign. Now you see that phi has to be less than equals to 1. Why? Because phi is nothing but, just recall what is the definition of phi. Phi is nothing but starting from 1 s to the power t0 for s lies between 0 and 1. Okay, that is what basically we have taken. Now if s lies between 0 and 1 and t naught only takes the positive integer values, so that s to the power t naught always lies between 0 and 1. So clearly expect, when I take the expectation of that also lies between 0 and 1. So I can also put 0 in this side. Okay. So now if I take the positive sign here, okay, if I take the positive sign here, so take positive sign. So then what happens? Phi is same as 1, phi s is same as 1 plus root over 1 minus 4 p PQS square divided by 2PS. Now if I take S goes to 0, S goes towards 0, what happens? That see that the numerator actually converges to 2, because this quantity goes to 0, this is 1 plus 1, so converges to 2, but the denominator converges to 0. So, this whole quantity converges to infinity, okay? Whole quantity converges to plus infinity, and that cannot happen because phi has to lies between 0 and 1. Okay, phi has to lies between 0 and 1. So, the positive sign I cannot take. So, only possibility is that I have to take the negative sign here, and finally, so I have phi s is given by 1 minus root over 1 minus 4 PQS square divided by 2 PS. And if now you take this quantity s goes to 1 here, if you take s decreases to 0 here, you will get phi s converges to 0. You will get that. You can check this one. Okay, you have to use the L'Hospital rule. That's it. Okay, so now. So that means I have to take the negative sign here, and the final expression of phi s is given by this for s lies between 0 and 1. So now if I just expand this particular square root in terms of power series, I have this particular expression. Okay, and now if you just collect the coefficient of s, coefficient of s square, so on and so forth, you will get, it turns out to be ps, then s square is not there, so 0 times s square plus pq square s cube, then you will have 0 times s to the power 4, and it goes on that way. Okay, so now if I collect that, the coefficient of s will be nothing but probability that t naught equals to 1 under the condition I am starting from 1. So that says that clearly says that p1 t naught 1 will be nothing but p, because it is the coefficient of s here. Okay, that is p. Then p1 starting from 1, p naught equals to 2 is 0, because the coefficient of s square is 0. Then p starting from 1, that p t naught equals to 3, the coefficient of s to the power 3 is pq square. So, it is pq square. Then p1 t0 equals to 4 is 0, and so on, it is going on. Okay. So, this way we can find out the expression of that all the probabilities of the form p1 t naught equals to n for different values of n. These quantities now we know for different values of n equals to 1, 2, so on and so forth. All those things we know now, and so using moment generating function and then using strong Markov property as well as Markov property, we actually able to solve this problem. Okay. Now another important thing, we can look into this probability, and as I pointed out, as s goes to infinity, s goes to 1, phi s converges to this probability. So let us try to find out this limit, and when I try to find out this limit, that is nothing but this s is basically 1, this s 1 I can put, this turns out to be that. Now if you put that p plus q equals to 1, which is basically p plus q equals to 1. If you use this relation, then this particular quantity can be written in this form. This particular thing can be written in this form. I again left it an exercise. So, you just remove this q with p minus 1. Okay, 1 minus p, sorry, you replace this q with 1 minus p here, you will get this one. So, just check it, you will get this quantity. Okay. So, what does this tells? It basically tells that if p is less than q, which is basically equivalent to say that p is less than half. If p is less than half, less than equals to half, that means p is less than equals to q. Starting from 1, it is sure that we will hit 0. Okay, starting from 1, it is sure that we will hit 0. So, if a population follows this kind of evaluation of the Markov chain, then if the population start from 1, it is sure that population will extend if p is less than half. Notice that p is basically nothing but probability of birth. Okay, and if p is greater than half, then there is a positive probability in the finite time we will hit 0, but there is also a positive probability that starting from 1 the chain will not hit 0. Okay, so now there is two possibilities are possible. Okay, both the things are possible, that in finite time I may hit, in finite time I may not hit, and both the cases we have some positive probabilities. Okay, now another point we have discussed, that again we can find out this expectation by taking the derivative first and then taking the limit. And so when we are looking into this one, you note that I have to only look into this. The reason behind that is that in the second case, in this case, there is a positive probability P1 t in 0 equals to infinity is 1 minus P by Q if Q is greater than if Q is less than P. Okay, if Q is less than P, that basically means that P is greater than half. Okay, so there is a positive probability of having this thing. So that basically means if I now try to under the condition that Q is less than half, P is less than half, under this condition if I try to find out what is the expectation of T naught starting from 1, it has to be infinity, because infinity times some positive probability will be there. So that has to be infinity, there is no question. So only interesting part is to look into this part, and so we are only for try to find out the expectation under P is less than half, again which is equivalent to P is less than equals to half. And so what I have to do, I have to first find out what is the phi prime s, and if I can find out this, I can take the limit. Okay, s increases to 1, if I will take the limit. So to do this one, I start with this. This is nothing but same as what we got here, that phi s is what we got here. Okay, this is nothing but same as this that I have written, and now I take the differentiation on both the side of this equation with respect to s. So if I do this turns out to be 2 phi s, this part I keep as it is, then the derivative of this function, which is basically 2 times phi prime, because phi is a function of s also. Then I take p phi s square is there, and derivative of s, that give me this, minus derivative of phi, and finally derivative of qs, which is q. Okay, and which has to be equals to 1. Now from here I can solve for phi prime, and it can be shown that phi prime is given by this expression. Now take the limit s goes to 1. Now take the limit s increases to 1. Now you just remember that limit s increases to 1, phi of s, this quantity is 1 if P is less than equals to half. This we have done here. Okay, this we have done here. This is 1. So I just phi square is 1. I replace, then P plus Q is 1. Then this phi is 1 and S is also 1. So it turns the limit in limit. It turns out to be 1 by 1 minus 2p, which can be written in this particular form also, that basically this is nothing but 1p you write in terms of 1 minus q. Okay, so you get this particular expression. So that means we get that this expectation of t naught under starting, when I am starting from 1, is same as 1 by q minus p for p is less than or equals to q. Let us look into this. What does it mean? This means that both the expressions are fine. So this means that if p is so in this case what happened? P is less than or equals to half. So if p is close to 0, that means this quantity will be small. Okay, this expectation will be small. If p is close to 0, then expectation will be small, and that basically means the difference between q and p is quite high. On the other hand, if p is close to half, then this expectation will be large, and in fact when p is equals to half, this expectation is infinity. So that means if the difference between p and q increases, that expectation actually decreases. So that means if p is close to 0, that means if the bar probability is very small, then on an average very quickly we will hit 0 starting from 1. And if the birth probability is close to half, then obviously it surely will hit 0, but the mean time to hit 0 starting from 1 is increasing, and if p is equals to half or greater than half, then the from starting from 1, the mean time to hit 0 is actually infinity. Okay? So, with this interpretation I stop here. Thank you for listening.